Hi, my name is Evan Boyd. In today's lecture, we will be talking about how to calculate the bubble point and dew point in a binary chemical mixture. Now, first, you may be wondering, what is the dew point and bubble point? It's a great question. Now, bubble point and dew point are just points or phases in the chemical mixture where you will see the first signs of the chemical mixture changing phases into solid to get solid to liquid, liquid to gas, gas to liquid, things like that. So for example, if had a pot of water we're boiling in, and you see the first bubble come out from the kettle, that is indication that the temperature in that kettle for the water has reached its bubble point, where you start seeing physical change of vaporization happening for liquid water. And then vice versa, if you're condensing water, you're condensing liquid vapor down to back to a liquid. The first droplet would be the dew point in this instance, where you see the first sign of the vapor transferring back into a liquid. So next, how we calculate this change. So we have a formula called Raoult's law. Which basically tells us that the concentration in species 1 or 2, we use species 1 in this instance. So species 1 of the liquid phase, so the concentration of liquid species 1, the liquid concentration of species 1 times the vapor pressure in the mixture is equal to the vapor concentration of species 1, so Y1 in this instance, times the pressure of the system. So now, how do we calculate bubble and dew point? Well, we'll use these equations to calculate both bubble and dew point, and they're very much similar. It's a little bit different from how we use the liquid concentration and the vapor concentration. So first, I will start with the bubble point. Now, this is an important step that we are calculating first the bubble point at a constant temperature. Constant temperature. Or the temperature as T. So we can also calculate the bubble point at a constant pressure, but you will need first the pressure at a constant temperature for you to calculate the bubble point at a constant T. So we always start with pressure first. Calculating the pressure first. So let's use our Raoult's law. So X1 Pvap equal to Y1 and then. So a keynote for this is that we know when dealing with Raoult's law, we have a binary mixture, 2 species in the mix, that the concentration of the liquid species 1 in the liquid form plus the concentration of liquid species 2 in the liquid form will always equal to 1. So if you had, for example, benzene and toluene, and you only had 0.3 benzene, 0.7 toluene, still equals up to 1. You always have a whole, either different molar fractions of the different species. It can be 0.5, 0.5, 0.2, 0.8. It will always equal to 1. And that's same for vapor concentration. So Y1 plus Y2, vapor concentration species 1, vapor concentration species 2, it's always equal to 1. Okay. So right here, we would want to get Y1 by its side first. Since we're dealing with a bubble point, that means it would be the first point where the liquid sees its first bubble into vapor. So the pressure by its vapor concentration by itself, divided by P, you have Y1 equal to X1 Pvap over pressure. Now, like I just mentioned, make it so we have more space. The sum of this expression will always have to equal to 1. So we can substitute the 1 in for the concentration vapor. And this will give us 1 is equal to the sum of liquid concentration times vapor pressure divided by pressure. All right, simple. Now, since we have 1 here and we're trying to calculate the pressure, we just need to put the pressure on it by itself. Easy peasy, and that's it. So multiply both sides by P. Final cancel out for this side, multiply by P. You have pressure is equal to the sum of the liquid concentration times vapor pressure. So easy P. All right. And that's how you find bubble point at constant T. Now, if you're trying to find the bubble point at a constant P, you will use the pressure that we just calculated here. Mass that we calculated here. I'll put it back in the formula. So we'll do, so this is the expression P is equal to X1 evap. So all you do here to find the temperature is put this and basically find the differential from the calculated bubble point that we use for a constant T minus the pressure that the mixture is already in. So we have a pressure differential, P. And since this is our known value and we have an unknown T, we will need to use a solver to check and guess what temperature T would be. So this is when you need a TI-84 or you use Python, which we'll use later. So you would take this expression, plug this into your calculator, and then T will be your unknown. Check and guess what T would be until it aligns to where your pressure that you calculated aligns with the temperature that you're guessing, and you'll find your temperature. Okay. So now let's do the dew point. Now, dew point is very much similar to the bubble point. Same way we start with Raoult's law, also mentioned we always start constant T first, so dew point at constant temperature. So start with Raoult's law again. I'll use species 2, switch it up so we don't have to keep using species 1. So I don't know if you can see. Liquid concentration in species 2 times the vapor pressure equal to liquid concentration in species 2 times pressure. Now, a dew point, like I mentioned earlier, is the first sign of the vapor condensing down into the first droplet of a liquid. So here we want to isolate X first, or liquid concentration first, since we know so first P1. So we will do divide this is greater than my P vapor pressure, the vapor pressure. So we'll have X2 is equal to liquid concentration times pressure divided by vapor pressure. Again, mentioned here, we know that the sum, we know that the sum of this expression will have to equal out to 1. So we replace the 1 with that. The liquid concentration, we have now 1 is equal to sum of Y, liquid concentration, times the pressure divided by vapor pressure. Okay. So as we know, we want to find the pressure. As we're trying to find pressure, so we need to isolate the P by itself. Now, the easiest way to do this is just to divide by P on both sides. Cancel this out here, so you have 1/P is equal to sum of Y of vapor concentration over vapor pressure. And then just to the, you can flip both sides. So this be, times by to the 10th. Oh, let's go down, divide by 1 again. Should be P is equal to the sum. Will be equal to 1 over the sum of Y. Liquid concentration, no liquid concentration, plus species 2 divided by the vapor pressure. And that is it. And then be the same way how you solve for pressure, temperature at a constant pressure. You'll use the pressure that we calculate here for dew point. Put this into a solver. So this will be your known variable. And then you have unknown as T. That's in check, and that'll be it. Okay, so now let's move on to our coding part. So let's now go to the calculating the bow point and dew point for in Python. So I'm using Colab. You can use any type of Python version you want, but for me, I'll be using Colab because it's on Google Chrome. This is on a web browser. It's easy to access. So first thing I'm doing is I'll be using this. So this is a web page that has multiple when it has props, chemical formulas, things that we need to run this equation. So anytime I'll do a prompt, I'll be using this website. You can copy this if you want to follow along. It'll be easy for you to understand the tutorial better if you use this. But yeah, from this, we will first start with pulling this information from us. So importing import MB. So from import MB, we will import notebook. Okay. With notebook. And then, oh no. From import 25 import props. You saw it to you there a little bit, but basically all this is saying that so from the website we are pulling a section called notebook, and then in this notebook, so with the notebook, we are pulling a section called CHE5, which has the chemicals that we need, like water, toluene, benzene, stuff like that. A whole list of chemicals that we'll be using. Taking that section and importing the props, which is the actual chemicals. So as I was saying, and the props is what we'll be using to illustrate for the chemicals. So to pull out chemicals, we'll be using the props. It has local weight, boiling point, vapor pressure, stuff like that. So perfect what we need for this equation, for this calculations. Okay. Next thing we'll be using is pulling the Python library numpy. So import numpy make it easier for us. We're going to decide about the whole thing every time. And then the last thing we'll be using, which is it'll help us for calculating temperature, or bubble point temperature and dew point temperature, is a thing called SciPy optimize. And root. So spicy optimize. SciPy optimize is another library in Python that we can use. And then the root function is basically basically a solver. So basically like a TI 8485. It's a solver you use to pop out to find unknown variables. So in this route, it would take it's good for using vectors. So you take a known vector and an unknown vector. You put a guess in, it comes together and spits you out a number. Basically all root is. And but this can do it for a magnitude of unknown and known vectors. So it's very helpful if you have a lot of vectors, a lot of known and a lot of unknown vectors. If you just need shoot out guesses, roots perfect for you. Here we're just using one known and one unknown. So it'd be pretty simple for us. So this is all you need to import. Shift enter. We're all good to go. So let's go to our prompt. So this is what the prompt says. Derive the equation of solving bubble and new pressures in an ideal system at a constant temperature. Assuming that the binary system is benzene and toluene, our chemicals here, a binary mixture, behaves ideally, write a code to calculate bubble pressure, bubble temperature, dew pressures, and dew temperatures. And then here, 1, 2, 3, 4 says, liquid composition 30 as a or ratio 30 to 70 mole ratio of benzene toluene at temperature T370, 373 fit 0.15 Kelvin, calculate bubble pressure, calculate temperature, dew pressure, dew temperature. So they all have the same temperature. The bubble pressure, dew pressure are the same temperatures. They all have the same molar ratio, and we know that chemical composition. So let's put all this into a log. So first we need to pull our prompts. So we need to pull our chemicals that we're using, which is benzene and toluene. So we need to do P equal props, pull in this, pull in this. And then we'll use benzene. Oh, don't forget to put tallies, benzene. And then comma, you do for each chemical, and then toluene. All right. Better. So all you do. So all you do is do props, parentheses, brackets, and then put the chemicals that you need. Make sure you put italicize, either one italicize or double italicize to call out chemical. Next, we will be calling out the molar composition, molar ratio for the benzene toluene. So for this, we'll be using variable comp, for composition is equal to, see it chain again, I've been practicing this, as you can see, np.array, and the same thing, parentheses bracket, and we know is a 30%, 30 to 70 mole ratio, so 0.3. I do 0.3, comma 0.7. Okay, shift enter. You have that there. So now our first part is to find the bubble pressure. So now if we go back to your notes and we go through how we calculate the bubble pressure, we use Raoult's law, set y equal to 1, and then find p from our formula we created, and it should be pressure is equal to the x1, which is be the liquid composition times the vapor pressure. So first let's write out what we're trying to find. So we're trying to find the bubble pressure, and then for this you need to put ideal, and we're using the liquid composition, and then at a constant temperature. Okay. All right, and then we want this to return mp.sum. So the sum, all the arrays that we'll be collecting needs to be all the compositions in the middle of the composition, in liquid composition, times p dot p, okay, at a constant t. Okay. This is saying our equation is that so for all the sums, other sums or arrays I'll be pulling, the multiplication inside that we already created. The formula is electric composition times the vapor pressure. And it's taking each one, each array, each section. So throughout the composition, not throughout the array, because if you never looked at a bubble point, dew point graph, you can tell a curve. So each iteration, you'll pull this, take an array, sum it up. All the sums together will give you the bubble point. Double point. Shift enter. And then if you want to well, just see what we get. Bubble P underscore ideal. And we know the combination is comma, and then we were given that the temperature is at 373.15 Kelvin. If I can type that right. All right. Shift enter, and boom. So this right here is our answer. Now note that this answer is given in Pascal, so our pressure is 105,789 pascals. Okay. Quick and easy, simple. Okay. Now, the more challenging part about this equation, about this code is how to find the bubble temperature. Okay. Now it's kind of similar to how we just set it up for our bubble pressure, but it does shift off a little bit. So let's start off again. So defining bubble temperature for ideal. And for here, we're still using the liquid composition, but now we're using a constant temp pressure. Okay. All right. So we would start using like we would do this, but the only thing is that we don't really have, our temperature is a guess. So this is when we implement the root that we the spicy optimize with the root. All right, this is what will be important here. So we need to first find the pressure differential and pressure. So we need to do another define. Assign your define deviation in pressure. Okay. And this would be respect to T. And this, we want this to return. I cheated already, but you want this to return the bubble pressure that we calculated already, after the liquid composition and temperature minus the system pressure. So basically literally what we put on the whiteboard earlier. We the difference in pressure. So we're calculating the difference in pressure. And then this difference in pressure, we use the root now. Our solver here. So root bracket. We need to put a function. So first put the function you want to shoot in the solver. So P dev, so differential equation, and then we just have a guess. So a guess for our temperature. So you can start with 200. See where that goes. Okay. This back. Shift enter. All right. Now let's plot the bubble point at a constant temperature. Let's see if this is first correct. So with this now, this should first check if this is correct. What does it give us? All right, let's see. Oh, bubble. I spelled this wrong. Oh, what a shame. There we go. Oh, I just put it as a string. Okay, I forgot to put which is our molar ratio, and then a pressure. So we're using ideal pressure here. So 101.325 is ideal pressure at pascals. So enter. So this statement is true. And this is our answer. If we want to actually in our array, we would do dot x, should enter, and we get 200 for the temperature. Now, if we change this, I think it's a little bit too low. Change to 300. See what we get here. Bada bing, bada boom. We get 371.65 as our temperature. Now we can keep scaling this up and up. We can start 400, but we'll still get the same answer. Now, the lower you scale, the lower your number will get because it's at the max it can really go. It's not the true value. And so until you how to keep guessing and checking to truly find out what is your actual temperature. So that's what the solver, the root, basically acts like your solver here. All right, so that's basically it. Now the calculating the dew points is basically the exact same. You can just copy and paste. So let's copy and paste this. And instead of double P, let's put dew. Okay. The X will now be converted to a Y, so we're dealing with the liquid composition, silicon constant T, and then we're changing this to a Y. Okay, shift enter. And then we can solve for this. So do P underscore ideal, pound ideal, and then composition, comma, and then 373.15. Should enter. Bang. Pressure is 105,789.27 pascals for pressure. This I think is the exact same actually as our original. Oh, actually this is wrong. I just caught my mistake. So, if you just caught my mistake, I forgot to notice that in our equation is 1 over my y divided by p-vap. So it's a different equation. So it's a little bit different. So you just still do np dot sum, but you have 1 divided by y divided by p dot p-vap. Okay? That is important, and I'm sorry I missed that, but now we should be good. Shift enter, and we have a new equation. Yeah, so it's 705,403 pascals is our actual pressure for this ideal system, for this dew point pressure. Okay, so now let's do this for the dew point temperature. Okay, so let's copy and paste this from our bubble T. We will switch the bubble T with dew T for in the X with a Y for vapor composition. Oh, running out of time. Oh shoot. You gotta fix that then. Well, almost done. So for this still pressure differential, it will return the dew point P with a respect to a Y, still minus P, is still differential in pressure, and then return root P dev, and we can keep 400. And let's see if this works. Shift enter. Do T underscore pound ideal composition, and then in the pascals 101.325. We get 315.42 Kelvin as a temperature for our dew point. And that's it, ladies and gents. That's how you calculate the bubble point and dew point for our word problem. Hope this video was helpful, and I hope you guys have a fantastic rest of your days. All right, and see you guys in the next video.